Hello everyone, my name is Zichong Wang, and today I will be discuss our paper Prevent Discriminatory Decision Making in Evaluated Stream. We will be explore the following topics today: machine learning for data stream, challenge faced in this domain, and our model fair sampling over stream, and our evaluation model fairness boundary unity. And first, we will start with machine learning for data stream. What are the data stream? Data stream refer to the sequence to data that is continuously generated over time and a possible infinitive. Each item have a time step, so temporal order. And what is the machine learning for streaming data? Is data items are arrived one by one, and we would like to build an maintenance model, such as patterns or predictors of those items in real time. And we have a couple examples in here, like cybersecurity or marketing and e-commerce. And the next question is, why should we abstract the data as a data stream? They got two reasons. First, when you can't store all the data, and the second is when you don't want to store all the data. For the first one, the reason we can't store all the data because the data is continuously being generated and it's not necessary or particularly to store all of them. One classic example is social media platform like Twitter. There are millions of tweets being posted every second around the globe. Store all those tweets for all time would require massive amount of storage space and isn't necessary for most applications. And an example for we don't want to store all the data is in credit card fraud detection system. Credit card companies process millions of transactions every day, and each one generating data that could be useful for identifying fraudulent activity. However, it's not necessarily non-efficient to store every transaction every made. The majority of transactions are legitimate and do not contribute to deterring or prevent fraud once they will be verified. Furthermore, privacy regulation might restrict how long some types of data can be stored. And next, we will compare the offline and online. For the offline model, it will define the training phase, and you can render across to the instance. And the challenge usually we made is missing data or noise in the dataset, or dataset is imbalance. And for the online model, it's sequentially cross-only, and it has strict time and memory requirement, so you can't collect data today and training like later in the weekend. And it's usually non-stationary data distribution. And the challenge we usually make is inherit those from batch and the consorship draft and fairness draft. And here we make an example. We can say for the offline model, we got the training data and test data, and the output is the training model. And for the streaming data, we can say the training data and the test data is constantly happen. So we basically follow on the time, and the output is trainable model. And next is the assumption for our study. Our data is independent and identical distributed, which means the data we collect in the time t does not influence we collect in t+1. And we got another two things. It's immediate and delay. For immediate, the label for data we collect in time t is available before the next data coming. And for delayed, it means the label for the data we collect from the time t is later than the next data coming. And next, we will talk about the challenges. There are three challenges in here. First is computational, is restrict the computational resource, which is the memory and also the CPU and the GPU. And the second is the constant draft. The data distribution change over time, and the fairness draft. The fairness of model predictions may draft as the distribution of data change over time. And next, I will discuss our model. First of all, they got several algorithms for detection the constant drift. And in our model, we use adaptive windows. And we also use the synthetic model to recover from the constant drift and the fairness drift. However, existing cybernetic model used in machine learning computational extrapolate data imbalance. This is due to those model generation the number of samples in the majority class. Hence, the representation of the unprivileged group sample decreases after the data generation process. For instance, here is the example. Before the generation process, the unprivileged group is 33.02% in whole dataset, and after generation is 26.87% in whole dataset. And here we got another example, the SMOT, very famous generation model. We try to use it to generate a triangle symbol, as the picture shows. But we can say the synthetic generate triangle symbol fell into the error of circle symbol, result in the actually synthetic symbol belong to circle, which is the majority class symbol. Therefore, to overcome this issue, we first close the symbol, then use SMOT synthetic symbol within the each classes to avoid this problem. Additionally, we set up two thresholds. One we call performance threshold, that is for constant drift, and one is the fairness threshold, that is for fairness drift. And we can see the equation in here, which level 0 is equal to log 2 times log n divided by theta. The n is the window size, and the theta is the threshold. Also, we set the warning level by multiple theta by 10, so it will help determine the change level. The last thing I will talk about is the FBU. And the FBU is help us trade off between model performance and fairness. And the FBU have 5 effectiveness level. First is joint advantages, and second impulsive, and third reversed. And the first is deficient, and the last one is joint disadvantage. The logic behind FBU is that if everyone's decision is random guess, then there is no discrimination. Hence, as we increase the proportion of prediction label replacement, the fairer the model will be, and also the lower the performance will be. Here we have an example. So we can see in the figure A, the red line represents the fairness. So when we replace all the labels, the fairness is the highest, and also the performance is the lowest. Additionally, we will total have 11 points, which is the original point, and 10%, 20% until to the 100%. And based on those 11 points, we create the baseline as shown in figure B, like the yellow color line. And also, I will talk about how we can compare like two models. There are two models in figure B, which in model 1 is a green line, and model 2 is a purple line. As we can see, the area for model 1 is larger than model 2. So in this case, M1 is the better models. That's all for today. Thank you.